say welcome to everybody to this first class in our master class series, Practical Ways to Use Contemporary Statistics. We hope that you'll find some useful insights into the application of statistical methods for design and analysis of studies which clinical researchers conduct. Today we welcome Dr. Janet Wittes, who's a recognized expert in statistics as applied in clinical trials. She received her PhD in statistics from Harvard University, was on the faculty at Hunter College at the City of University of New York, was chief of the biostatistics research branch at the National Heart, Lung, and Blood Institute, and was also at the U.S. Department of Veterans Affairs for a time. And then in 1990 founded Statistics Collaborative, Inc. And I have worked many times with Janet over the years and visited FDA with her as well. So her research is focused on the design and analysis of randomized clinical trials, capture-recapture methods in epidemiology, sample size recalculation problems in clinical studies, and analysis of safety data from clinical trials. Her co-authored book, Statistical Monitoring of Clinical Trials, a Unified Approach, is widely used. Janet is a member of many advisory committees, including a large number of data monitoring committees. And she's been a former and current member of several FDA advisory committees. So she's also been the Society of Clinical Trials president, editor, and chief of its official journal. And so thank you very much, Janet, for agreeing to participate in this series. We're very much looking forward to your talk today on correlated data.
Well, thank you, Beth, and thank you for inviting me, and thank you all for being here. And Fatima, I want to thank you for helping with the making this work. I had all kinds of electronic trouble, and Fatima made it work, which is great. So I first want to say that although actually, Fatima, you can share your screen and put the slides up. She's going to be, I'm going to say change the slides because I couldn't get my screen to work. Thanks. So the original title said it was going to be correlated data in randomized clinical trials. But the more I thought about it, the more I realized that the problem comes up in all kinds of situations, both experimental and observational. And so I'm expanding it to be not only for randomized clinical trials, but for whenever you have data. And I hope that you all either appreciate now or will appreciate by the end of this morning. Oh, I guess this is evening for you. That when you're designing trials, or experiments in general, or studies in general, you should think about what is the nature of the correlation between various pieces of data that you have, if there's any correlation. That when you're analyzing the data, that analyzing correlated data, that you will analyze the data correctly. And when you're looking at other people's analysis of experiments, be they lab experiments or clinical trials, that you will appreciate whether or not they have done the analysis and dealing with the correlated data in a correct way. Next slide, please. So this is a picture of twins. It came from the web. I thought they were absolutely adorable, so I'm using them. These are not in a gene therapy trial. But my reason for wanting to discuss this issue arose because of a randomized trial that was assessing the effect of gene therapy in a very terrible genetic disease that led to very serious problems early in life and limited lifespan. In this trial, so the trial was designed, and it was a randomized trial of a intervention to a control, the intervention being a gene therapy and the control being just watching what happened. A pair of twins showed up, and the question was what to do with them. And the first question that arose, well, maybe we should just randomize them, and maybe they'll be on the same treatment and maybe they won't, but just treat them like anybody else. And then there was a discussion that said, no, well, that's not really right, because what if one gets the gene therapy and the other doesn't? And that would be horrible if the gene therapy works. It would be horrible if the gene therapy doesn't work. But the difference, having two identical twins getting treatments, very different treatments in a disease that was devastating, didn't seem fair. But my concern, which that of course was a very big part of my concern, but whether the decision was made to randomize them or to give them both the same treatment, we basically had two people who were so genetically close to each other that whatever results you got in one, you were very likely to get in the other. And so the decision was made, we'll randomize one, we'll see whether that one gets gene therapy or control, and then the other one will get the same treatment, but the other one will not be a member of the official sample size. He will just be getting the treatment that his twin got. And I realized that this kind of thing can happen frequently. It's not usual that you get identical twins, but that you get siblings or people that are very similar in other ways can happen in clinical trials. So what I'd like to do is talk about four things that first of all, to define what i.i.d is. This is going to be a fundamental concept that we have. Then talk about correlation in what I'm calling simple experiments. There's a sense in which no experiment is really simple, but structurally simple. Then correlation in longitudinal data, and then finally some conclusions. Next slide, please. So I'm making the assumption that all of you have some familiarity with basic statistical tools, that you know if you have two distributions and you want to compare their means, you can use t-tests. Or if the distributions are so far from being normal that the means from those distributions will not be normally distributed, that you can use some kind of non-parametric test. So that's that second bullet. Or that if you have more than two groups, or if you have at least two groups, but you have strata, you can use analysis of variance. So those are some of the very basic tools. Next slide, please. And another very basic tool is regression, where you're looking at the relationship between an X variable and a Y variable, and you asking whether the X variable predicts the Y variable. And in the graph that has the blue line with the red dots, that's linear regression. So there, the dots follow along a line, and in the curve on the right, it's a non-linear regression, that there's a very definite relationship, but it's not linear. Next, please. And then there's logistic regression, which is a little more complicated and not used. I would say it's the next level up in tools, where you have an x-axis, which is a continuous variable. Here is hours studied. And on the y-axis, you ask whether the person passed the test or not. And what you see is either the answer is failed, and that gives you a little dot at the bottom. That's so your outcome is 0, or you succeed, you pass the test, and then you get a 1. So the only outcomes are either a 0 or a 1, but your goal is to estimate the probability of passing the test as a function of hours studied. And as you see, the little dots get thicker and thicker. The top dots get thicker and thicker the more hours are studied, and to the right, and then the bottom thicker and thicker as the people didn't study. So that's logistic regression. And next, please. And then there's time to event analyses, where you're looking at a bunch of people that are starting at time 0, which is the way up at the top. And you're looking to see, you have an event that's occurring that you're interested in seeing when that event occurs. This conventional thing is death, but there's all kinds of events that could occur. And every time the event occurs, the curves drop down a little, and you want to see what is the experience over time of a population in 2 different groups. And that's a Kaplan-Meier curve, which I've displayed here. And you test them statistically, either with a log rank test or a Cox model, and there are other methods to do. So those are the basic statistical tools that we have. There are lots of others that are more sophisticated, but these are the basic tools. The important thing, next slide, or an important thing, is all of these tools rely on what are called i.i.d observations. In English, independent and identically distributed. And I won't show you how bad my French is, so I won't say it in French. But fortunately, both the English and the French have the same acronym, i.i.d. So they all rely on i.i.d. And very often, and this is actually the topic of this talk, is that people use these methods without asking, are my observations i.i.d? So what I'm going to do in this talk is define what independent is, define what identically distributed is, and then I'm going to say, we're not going to be dealing with identically distributed today. We're going to be dealing with independent, and correlation is related to that. So next slide. So what does independently distributed mean? The data need to be uncorrelated. So what are correlated data? Or in French, here they are in French. The definition of correlation given in the Merriam-Webster dictionary is a relationship existing between phenomena or things, or between mathematical or statistical variables, which tend to vary, be associated, or occur together in a way, and here's the important part, not expected on the basis of chance alone. So that's correlation. Next slide. In the statistical world, it's defined a little more formally. In statistics, correlation is any statistical relationship, whether causal or not, between 2 random variables or bivariate data, so that's an X and a Y. In the broadest sense, correlation is any statistical association, though it actually refers to the degree to which a pair of variables are linearly related. So, and I'm going to go back and forth for this linear and not linear. I'm thinking more, is there a relationship? Next slide, please. So now let's go to what independent means. So Imagine in my hands, I have a coin here and a die here, and I'm going to toss them. What is the, and let me just back up a sec. The reason I'm going into coins and dies and urns is that these concepts of independence and identically distributed variables come from probability. And early probabilists were really gamblers. So we know a lot of probability out of gambling theory. So what's the probability that the coin, which is here in my left hand, and the die, that the coin will show heads and the die will show 6? Probability of the heads is a half in a perfect coin. Probability of a 6 in a perfect die is 1/6. And because they are, that should be an N independent, not I dependent. The probability of having a heads and 6 is a half times a 6th or quarter. Next slide, please. Now, importantly, it doesn't matter if I toss the coin first and then the die, or the die first and then the coin, or the two of them together. The probability of the heads and the 6 remains a quarter. They don't talk to each other. They don't know each other. They don't learn from each other. They're independent. So that is an example of independence. Next slide. Now let's talk about identically distributed. Imagine now that each one of you has an urn. And in that urn, there are 3 red balls, 2 blue balls, and 1 green ball. And our experiment is that we each take out 1 ball and we look at it. And then we take out a second ball. Well, we take that first ball and we put it aside. We don't throw it back in our urn. We take out a second ball. What is the probability that the second ball is green? So we're all doing this experiment. So to get green on the second draw, we need to get a blue or red on the first and then a green on the second. So that probability, assuming the balls are all the same and we mix them all up, is 5/6. That's the probability of getting red or blue first times 1/5. And we multiply those together and it's 1/6. So this answer is the same for all of us. So this process is identically distributed. Next slide. But an important thing is that these successive urn draws are not independent. If we take it out 1 ball and look at it, if we draw the green ball first, we know that we have no chance of getting a green ball on the second draw because there's no green ball left. And if we don't draw the green ball first, the probability on the second is 1 out of 5. So they're not independent. They were identically distributed, but they're not independent. Next slide. So it's important to recognize as we move from these ideal situations, these gambling situations, the data can be independent, but not identically distributed. And that's my coin and my die. The coin and the die are very different, but they're independent. And they could be identically distributed, but not independent. And that's drawing from an urn that should, without replacing the balls. And importantly, for the standard methods of statistics, we need both. We need both independent and identically distributed. Okay, next slide. So what does i.i.d. now mean? i.i.d. is independent and identically distributed. So imagine you sit there and you're flipping a coin 100 times. And each time, the probability of heads is a half. You have a perfect coin. So even if I flip a coin and I get head, and then head, and then head, and then head, and then head, the probability of the next toss of a perfect coin is head is still a half. And why? Because the coin has no memory. Now, people would sometimes say in a situation like this, I'm due for a tail. No, coin doesn't know that it went head, 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 head. You're not due for a tail. Now, of course, if you had a coin and you kept on getting heads, you might say, wait a minute, this is not a perfect coin. I'm going to, I think my probability of the next flip being a head is more than a half. And now you're acting like a statistician. You're taking the data to make an inference. But the wrong approach is to say, I'm due for a tail and think your probability of a tail went up. So next slide. But suppose you did have a biased coin where the probability of the head is 0.6. Then again, each toss, the probability remains 0.6, and this coin still has no memory. So independence, you don't have to have the same probability, but you have to have independent probabilities. Okay, next. Now, what in the world does all this have to do with experiments or clinical trials? And as I said before, I'm going to focus only on independent, not on identically distributed. So how do we know that observations are not independent? The first example I gave you were those twins. We know they're not independent because we know biologically their genes are the same. And what do we do when we face non-independent, i.e. correlated data? And that's the topic for today. So next slide. And here's examples of perfect correlation. These all a correlation of 1 where I can predict either 1 or -1. 1 meaning that as x goes up, y goes up. -1 means as x goes up, y goes down. The point is that in each of these cases, I can predict with complete confidence, if I have an x, what will the y be? That's my correlation of 1. Next slide, please. As the data become less definite, as my prediction becomes less clear, so here's a correlation of 0.8, the one over to the left. There's some scatter, but the eye sees very clearly that there's it's trying to make a line. When my correlation is down to 0.4, the eye is having a little trouble seeing that there's a tendency, but if you look carefully, you can. And at 0, there's no probability. There's no relationship between your x and your y. And then the other 3 to the right are in the other direction. Next slide. Now here are patterns where the correlation coefficient is 0 because there's relationships, but you can't predict on any given x what the given y will be. These are uncorrelated data, very patterned, but uncorrelated. Next. And now we're going to move to experiments. The experiments I'm going to show you are, well, the first one is fake data, but it comes from an example that I faced really recently. These are the animals whose data I saw were not frogs, but they were eyes. So it's similar, but I use frogs because they have such wonderful eyes. We have 230-degree peripheral vision. They have 360. Some species have 360 visions. They can see in the back of their head. And they also can see color in the dark. So they're really quite remarkable. So we're going to talk about an experiment with 8 frogs. Next slide, please. So here is an experiment with 8 frogs. And here's how the experiment, 8 frogs and 16 eyes, each frog having 2 eyes. The experiment works like this, that each frog is taken and there's 2 treatments, there's a placebo and a treatment, and they are the treated group, the treatment is randomly assigned to one of the eyes. And so this is a placebo. Here's the results for the placebo eye. And this is the result for the treatment eye. These are fake numbers and they don't relate to any specific metric on the eye itself. But what we notice, if you look at the data, next slide, that the treated eye seems to do better. Than, I'm assuming that a larger number is better, that every frog, except for frog number 5, the treated eye did better than the placebo eye. And we also noticed that the numbers seem to be the same. We seem to be able to predict from the placebo eye what the treatment eye will look like, the measure. All right, so we can ask the question, and this is actually what was done for the experiment that I saw in a different animal, a different kind of animal. Next slide. So what you can do is say, well, I have placebo and treatment. I can take the means of the treated, the placebo, and I get 3.1, and the treated, and I get 3.5. I calculate the standard deviations, and I do a t-test, and it's not significant. And so I say that, well, those numbers looked pretty suggestive to me, but this is perfectly consistent. A p-value of 0.19 is really consistent with chance. So it looks as if I don't have strong evidence that the treatment worked. Next slide. But had I plotted my data, the untreated eye versus the treated eye, I would have seen a pretty strong positive relationship between the 2 eyes. Next slide. And if I fit a line, I would have, there's my line, with my least squares line, my correlation was 0.76. So those were pretty highly correlated. Next slide. And in fact, I don't have a sample size of 16. I have a sample size of 8. I have 8 frogs, and I have 8 differences between the 2 eyes. So here I'm taking always the treated eye minus the placebo eye, and I have an average of 0.4, and of course that's the difference, the same. If I took the mean of the placebo and the mean of the treatment, the difference between that is 0.4. But the difference is I now only have one standard deviation to worry about. It's the standard deviation of the difference, and that's 0.38. And if I do my test on the basis of the difference, because those 2 eyes on the same frog are highly correlated, I get a p-value of 0.02, which is saying there's pretty much, there's rather strong evidence that the treatment is better than the placebo. Next slide, please. And in this case, ignoring the correlation decreased the power of the test. Next slide. So here's a different experiment. I have, again, 8 frogs. I treat 4 of them, both with the right eye and the left eye. And I don't treat, and those are the yellows. And frogs 5 through 8, I don't treat. I get a mean of 3.8 on the treated frogs, and that's a mean of those 8 eyes with a standard deviation of 0.41. And in my untreated eyes, I have a standard mean of 3.2 and a standard deviation of 0.59. And I do my t-test, I get a p-value of 0.02, strongly suggestive of a benefit for treatment. But wait a minute, I ignored my correlation. Next slide. Because the 2 eyes in each frog are correlated. They come from the same frog, so they have relationships between them. And so I'm now interested in characterizing the frog, not each eye in the frog. So what I have is 4 observations, 4 treated frogs, and I take the average of their right and left, and I have 4 untreated frogs, and I take the average of their right and left. And now, again, my mean is the same, 3.8 versus 3.8. That's the distributive law of arithmetic. And my mean in the control is the same, 3.2 and 3.2. But again, my standard deviations are different. And now, when I do my t-test, I get a 0.11 for my p-value, which is, it's suggestive, but not conventionally statistically significant. So now what has happened, that by ignoring my correlation, I've increased my power, right? Because I acted as if I had 16 observations, but I really only had 8 independent ones. So next slide. And this kind of happened. So, right. So here, ignoring the correlation gave us false precision. In the previous case, ignoring the correlation gave imprecision, right? Now it gives you false precision. Next slide. So this kind of correlation happens a lot. So in sunscreen tests, what you do is you take somebody's back and you split it into lots of little pieces, and you do either you do different sunscreens on the different parts of the back, and you then you expose the person to sun, and you ask which sunscreens have worked the best. There, you have to take into account the fact that it's the same person's skin, and you have to take that correlation into account. The first time I saw an experiment like this, what had happened was they took people, this was a sunscreen experiment where every person had 8 little sections on the back, and some people were given one sunscreen and some people were given the other sunscreen. And what this experimenter did was just like what my fake frog person did. They took the 8 observations as if they were independent and took each observation from the back as an independent observation. And so they had 8 times the number of observations as they had people. And that was false precision. You'll see this very often. Plaque in coronary artery segments. I've seen experiments where they'll take the same person, the same segments, and then treat them as if they're independent observations, which they're not because they're in the same person. Skin lesions, same sorts of things. So what you have to think about is that measurements within a unit are in general correlated. Whether it's a person, an animal, a plant, a thing, if it's within the same unit, they'll tend to be correlated. Next. So here's another one. If you, and you'll see this in the educational literature a lot, experiments comparing teaching methods You randomize the classroom. So you have 30 kids in the class and 30 kids in another class, and you have different teaching methods. And then they'll take the individual student as the element, as the observational unit. But it's really the classroom that's the observational unit. So those are highly correlated data, and you can get huge sample sizes because unfortunately classrooms are often large, but you really have very few independent observations. Laboratory animals that share the same cages, another kind of example. Or surgeons in a specialized surgery where it really matters what surgeon you go to, the outcomes within a surgeon are correlated. So you have to think about what is the nature of the unit that you're looking at. And now I want to switch to another kind of correlation, of correlated data. And this is in some ways much more complicated. Next slide. And all of the examples are going to give you come from real observations with real, these come from almost all randomized trials. Some of them, one of them doesn't. And where you're looking at data over time and you're looking to see, is one treatment better than another? And here you have two treatments. This is, most of these are pain examples. So this is an example of pain. It looks like one curve is consistently above the other. And these are the standard errors, which are very wide, but the conclusion of this study was that there was no difference between the treated and between the two methods of treatment. And yet when you look at the data, at the picture, you said, well, wait a minute, one is consistently above the other. Why is it that there's no difference, that the statistical methods can't identify a difference? Let me show you another one that really you can see. Let me see the next slide. And this is actually visual acuity, and the x-axis is time, the y-axis is the number of the difference in letters read compared to baseline. And you'll see a very strong difference between the two groups. Importantly, and if you go back to the other slide, yeah, you'll notice in the bottom here, you don't see any sample size. So you have no idea when you look at this, whether the number of people stayed the same over time. You assume they did because the standard errors seem to be similar, but there's no ends. Next slide, back to my, yeah. Here it's really important. All the numbers are there, so you scan the numbers and you realize, yeah, pretty much these are the same people. I'm looking at the means and the standard errors over time for each person, for the set of people, and it's the same people. But underlying all this, next slide, are the individual people. And so here is a graph that shows what we were seeing in the previous slides was the resolution of the data after there was all the means were taken. But really, underlying is a bunch of, these are spaghetti plots, a bunch of people over time, and each of these observations within a person is correlated. So I have correlated data over time, and I'm averaging over that. Next slide. And here is now a spaghetti plot where there's two trends that are pretty obvious, and you can see the blue is consistently above the red over time, even though if you look at the strands of spaghetti, some of the blues are below the reds, some of the reds are above the blues. But again, the the component data are correlated. The component data, the individual people are independent of each other, but the data that they're contributing are dependent or correlated. Next slide. Now, sometimes, even in these complicated longitudinal data, you don't need elegant statistics. And there's a wonderful quote by Ernest Rutherford, the physicist, which, of course, statisticians don't like this. We statisticians don't like this quote. But if your experiment needs statistics, you ought to have done a better experiment. That's Rutherford. This is a visual analog scale where the left is I'm a no pain, and the right is the worst possible pain. So next slide. So here's a curve, a pair of curves where the score goes from 0 to 5, and you'll see these are the means, and it's pretty obvious looking at this that the group G has much more pain in the beginning, but the patterns are different. Group E, the pain gets worse over time, and then the two of them are the same. What this has, in addition to what the others had, the other two graphs, were the little stars above the first 3 points. And those little stars say these are statistically significant. We don't know here how they calculated the statistical significance, but we can tell that we didn't really need the experiment. These differences are so great that it's very clear what's happening. But now let's go to the next slide. This is another pain after surgery. This now has a visual analog scale that goes up to 10 to 100. And what you see, and these are two different methods of treating the pain. And what you see here is the top curve gets really bad and then comes down, and the bottom curve sort of gets a little bad and then goes down slowly. But the top curve, if you have to choose which curve you're in, you wouldn't want the top. But there's something very funny about this. There are these little stars in everything except week 42. So if you take what this report said seriously, you would say, oh, my pain is worse, or is in my PCI-A group, my pain is better, except at week 42. Well, clearly that doesn't make sense. There's something really funny about that. And I would say what's funny is two things. One is that the analysis didn't take care of the correlation within the person. And two, these are, and I think you're going to have a talk about this soon, these are measures testing over and over. There's a problem of multiplicity. You're testing over and over, even though it's the same curve. So we have to worry about, in longitudinal data, the correlation within a person, because the fundamental data are the observations over time within a person, and how you think about what you're trying to ask, and whether you're asking one question, which is my PCA, is my pain better on PCI-A overall? Is my pain better, or is it better at different times? But you have to be able to specify exactly what your question is so you don't run into multiplicity. So next slide. So what do you do with longitudinal data? Remember that these are highly correlated data. Each person's measurements are correlated within themselves. There's a temporal pattern for each person and a temporal pattern overall. You have to ask yourself, what are you interested in? Are you interested in what happens at the end of the study? Are you interested in the area under the curve? Are you interested in the trajectory over time? And these are all different. And I would say, while in those first examples that I gave, I think all of you can do your statistics by yourself. When you're dealing with longitudinal data, call one of us because they're really complicated. Next slide. Now this is my conclusion. Whoop, it's gone. All right, well, let me say what my conclusion is. Data are often correlated. If you ignore the correlation, you can overestimate your effects sometimes. You can underestimate your effects, and you can get the wrong answer. So you've got to take care of correlation. And if you do have correlated data, make your analysis fit the data. But if your correlation is very low, you don't have to worry too much. And with that, are there questions?